Hi, is my screen visible?
Yes, it is. Do you hear me?
I can hear you.
Okay, yeah, it's visible. Can you yeah, okay.
The title of this talk is Reward, Punishment, Symmetric Universal Intelligence. I'm Samuel Alexander from the SEC, and this is joined with Marcus Hutter of DeepMind and ANU. A little bit of background, which is probably not necessary for this crowd. In 2007, Legg and Hutter distilled the essence of intelligence into a universal form of reinforcement learning, or RL. They proposed to measure agent pi's universal intelligence, upsilon of pi, as its average reward over all suitable environments where each environment mu has weight 2 to the minus Kolmogorov complexity of mu. And this, of course, depends on the choice of a prefix-free universal Turing machine in the background. Now, in 2015, Legg and Hutter noted that the dependence on the prefix-free universal Turing machine choice is non-trivial. Different prefix-free UTMs yield radically different universal intelligence measures. They asked, what are other desirable properties of a UTM? This is a very profound question because a UTM basically is a programming language. So the real question here is, what are inherently desirable properties for a programming language? Not subjectively desirable properties like whether white space matters or whether we use curly braces or square braces, but what are desirable properties of a programming language that would be desirable even to aliens on the opposite side of the universe? In our 2021 paper, we made some progress, and the way we did so was we considered how would the intelligence of an agent change if rewards and punishments were swapped for that agent? And this leads to the notion of dual agents and dual environments. I define the dual pi bar of a reinforcement learning agent pi to be the agent who acts exactly like pi would act if all rewards sent to pi were intercepted and multiplied by -1. You can think of pi bar as being the masochistic alter ego of pi who seeks punishments and runs away from rewards. And whatever ingenuity and creativity pi possesses and uses to seek rewards, the dual of pi uses that exact same ingenuity and creativity to evade rewards and seek punishments. Likewise, the dual mu bar of a reinforcement learning environment mu is the environment identical to mu, except that all rewards are multiplied by -1. And this leads to a certain intelligence axiom. We define what we call Janus agents. A Janus agent is a reinforcement learning agent pi, such that pi equals pi dual. So it's an agent who is self-dual. This is named after the mythical Roman deity of duality, who supposedly has two faces, one facing forward and the other facing backwards, so that if you rotate him by 180 degrees, you don't change him. Definition: suppose you have any performance or intelligence measure upsilon, so the upsilon of pi measures pi's weighted average performance across all environments using some environment weights, then we say that upsilon respects Janus agents if the following axiom holds. For every Janus agent pi, upsilon of pi equals 0. Now, if we think of upsilon as measuring intelligence of the RL agent, this axiom seems very plausible, because if pi is a Janus agent, a self-dual agent, in some sense, that means pi doesn't actually know whether pi is wanting to get good positive rewards or whether pi wants to get negative rewards. You might imagine a Janus agent as an agent who sees the rewards from the environment as red and blue numbers without signs and doesn't know whether it wants to get the red numbers or the blue numbers. That's how you might think of a Janus agent. And it seems quite clear that such an agent would have no hope of performing well, because it doesn't even know what performing well means. So this axiom seems quite plausible, but it turns out that this very weak seeming axiom has a very strong symmetry result. Theorem: if epsilon respects Janus agents, then for every pi, not just Janus agents, but for every agent pi, the epsilon of the dual of pi equals minus the epsilon of pi. And there's a very beautiful proof, a very beautiful informal proof for this, which we're working on formalizing in a paper under preparation. Informal proof: fix pi, any agent at all. Let rho be the agent who, at the start of each environmental interaction, flips a coin and transforms into pi if the coin lands heads, or transforms into pi bar if the coin lands tails. Notice that there's only one coin flip per environmental interaction. The coin is flipped at the beginning, and then rho transforms into pi or pi bar, and then there isn't any more coin flipping. It's not that the coin is flipped every turn, rather there's just one coin flip at the beginning, and rho transforms into pi or pi bar. Now, since epsilon measures average performance, epsilon of rho should be the average of epsilon of pi and epsilon of pi bar. We assume the coin is fair. But by symmetry, rho equals rho bar, i.e. rho is a Janus agent. And we're assuming epsilon respects Janus agents, which means epsilon of rho equals 0. Now, by basic algebra, epsilon of pi bar equals minus epsilon of pi. A strong symmetry result following from what seems like a very weak plausible axiom. Now, one of the things that we had to point out in our paper, which is often brushed beneath the rug in a lot of these intelligence papers, is that RL environments don't map finite binary strings to finite binary strings. Rather, they map RL histories to reward observation probability distributions. And those are not finite binary strings. So therefore, to be pedantic, the Kolmogorov complexity of an environment actually depends not just on a UTM, but also on an RL encoding, a way of transforming the inputs and outputs to finite binary strings. And this is very important because the whole theory of Leghooder intelligence depends very strongly on the prefix freeness of the universal Turing machine and all the resulting benefits of the prefix freeness, which all depends crucially on things being mapped from finite binary strings to finite binary strings. Now, with that in mind, the Kolmogorov complexity is defined as you would expect, given a prefix-free UTM-U and an RL encoding C for encoding the inputs and outputs of environments. For a computable RL environment mu, the Kolmogorov complexity of mu is the length of the shortest computer program in that UTM-U for the C encoding of mu. And then we define U is C symmetric if for all computable environments mu, the complexity of the dual of mu equals the complexity of mu. Now, that bottom line on the slide there is much more interesting than first meets the eye, because this is an inherently desirable property of UTMs in the RL context. Aliens on the far opposite side of the universe might find this just as desirable as we do. It's inherently desirable, not subjectively desirable, like whether or not white space should matter or something like that. Within the context of RL, this is an example of an inherently desirable property for UTMs. A symmetry requirement that each environment should have the same complexity as the dual environment. And we show that if the Kolmogorov complexity is so symmetric, then the Leghooder intelligence measure inherits some symmetry. First, a theorem. If RL encoding C is suffix-free, which is a technical condition, which would be of interest to AIT researchers, obviously, there is an effective procedure for modifying any given prefix for UTM-U to make it C symmetric. Then the Leghooder intelligence measure, which Marcus introduced in his talk at the very beginning today, is the measure epsilon, which measures weighted average performance, where for the weighting, you give each well-behaved environment mu a weight of 2 to the minus Kolmogorov complexity of mu, then our theorem is that if the UTMU is C-symmetric, in other words, if the Kolmogorov complexity of every environment equals the Kolmogorov complexity of that environment's dual environment, then Legg-Hütter intelligence respects Janus agents and thus satisfies Legg-Hütter intelligence of the masochistic alter ego of pi equals minus Legg-Hütter intelligence of pi. And although we didn't realize this when we started working on this paper, this is one of these things that once you realize it, it's blatantly obvious and you think, I should have seen that long ago. We realized there's an implicit bias in reinforcement learning. And our procedure for turning UTMs into symmetric UTMs works by debiasing. You see, RL researchers have arbitrarily decided that positive is good and negative is bad. Hence, they use the word reward. It would be just as valid to decide negative is good and positive is bad. And then instead of using the word reward, you would use the word cost. Obviously, these two versions of RL would be completely identical to each other. You just multiply everything by -1. Our symmetrizing procedure for symmetrizing a UTM can be thought of as constructing a new programming language given a given programming language, where every program in the new programming language starts with a bit specifying which of these two RL conventions the program is meant for. And you need this suffix-free requirement because in order to actually carry out this construction where you add the bit at the beginning of all the valid programs, you need to be able to unambiguously interpret the programs in the original language, and that's where the suffix freeness requirement comes in. As another example of an inherently desirable UTM constraint, we talk about permutations. A prefix-free universal Turing machine, we say, is C-permutable if for every permutation P of the finite RL action space, then whenever mu prime is the environment obtained from mu by permuting actions using P, then the complexity of mu prime equals the complexity of mu. Then just as above, using all the exact same reasoning, if C is a suffix-free RL encoding, then any prefix-free universal Turing machine can be transformed into a C-permutable universal Turing machine in an effective way. And for the corresponding Legg-Hütter intelligence measure, action permutations preserve agent's intelligence. And that seems very desirable because it would be strange if you gave me an agent and you said that this agent has genuine intelligence, and then I swap some keys on the keyboard and the agent's intelligence changes. That would mean that the agent's intelligence was somehow tied to the layout of the keyboard, which is not what we think of as something that should apply to a universally intelligent agent. Now, more generally, outside of the RL context, in general, symmetry, different examples of symmetry in Kolmogorov complexity give examples of inherently desirable UTM constraints in various different contexts. For example, suppose you have a function f which takes a string of text, and this function f has the following properties. For any English text x, f of x equals a canonical French translation of x. And for any French text x, f of x equals a canonical English translation of x. And for any text x, f of x equals x. So you apply it twice and you get back where you started. Then in certain literary contexts, the axiom Kolmogorov complexity of x equals Kolmogorov complexity of f of x might be inherently desirable. For example, if you want to know the complexity of a poem, but you don't care if it's a poem in English or French, you want to know the complexity of the ideas in the poem. And you don't want that to be affected by whether the poem was in English or French, then this Kolmogorov complexity symmetry might be an inherently desirable UTM property. Some future work, say that UTMU is C-symmetric except for mu if the Kolmogorov complexity of mu bar is not equal to the Kolmogorov complexity mu, but the Kolmogorov complexity of nu bar equals the Kolmogorov complexity of nu for all nu not in mu bar, then if so, for any self-dual agent pi, in other words, for any Janus agent pi, the Leigh-Hutter intelligence epsilon of pi is determined entirely by pi's performance on mu, and pi's performance on any other environment doesn't matter because all the other environments cancel each other. This allows explicit calculation of non-zero Leigh-Hutter intelligences. Choosing mu and pi carefully, these results shed light on the nature of intelligence. For example, you might wonder, can we choose our UTM such that the set of possible intelligence levels is dense in 0, 1? And we can answer that affirmatively by using these ideas. That's just one example of the applications of this, which we'll explore in future work. To summarize, the dual of an agent is the version of that agent which swaps rewards and punishments. So the dual of Samuel Alexander, that's me, is the version of Samuel Alexander who seeks punishments and runs away from rewards. And the Leigh-Hutter intelligence ends up being symmetric if the background UTM is symmetric, i.e. if the Kolmogorov complexity of the dual of any environment equals the Kolmogorov complexity of that environment. And this symmetry requirement is an example of an intrinsically desirable property of UTMs, aka programming languages, at least in the RL context. It's not subjectively desirable, like the question of whether white space should matter or whether we should use curly braces or square braces, but it's inherently desirable and would be desirable even to aliens on the far opposite reach of the universe who use different kinds of programming languages than we do. That's everything I wanted to say about this. Thank you for your attention. I'd like to open the floor to questions.
Thank you. Hello, can you hear me?
I can hear you.
So I have a small technical question. So you have these k mu bar equals k mu. Is that exact equality or equality up to a constant?
That's exact equality. And the reason you need exact equality is because when you have exact equality, then that allows you to simplify the infinite sum which defines Leigh-Hutter intelligence. And if it was only equality up to a constant, this wouldn't help you whatsoever. Even if it was exact equality up to plus or minus 1, it wouldn't help you at all because the whole point is to simplify the infinite sums.
Okay, so yeah, that answers my second question, which was going to be that I assume this holds up to a constant for all UTMs because it's really easy to transform one into the other. But so you need exact equality. I guess that's okay. Thank you very much.
Right. Yes, but that fact that it's easy to translate one to the other is kind of crucial for our proof that there's an effective way to turn any given PFUTM into a symmetric PFUTM.
I have a very basic question. In point 2, is it just an if or is it an if and only if?
It's an if. It's not an if and only if. In other words, if the Kolmogorov complexity is symmetric, then the Leigh-Hutter intelligence is symmetric. But we have not explored the opposite question, the converse. And if I had to make a guess off the top of my head, I'd guess that it's not true. I'd guess that it's probably possible to cook up UTMs which are not symmetric, but where the Leigh-Hutter intelligence is symmetric. But that's only a conjecture, and I don't know the answer as for the converse.
All right, other questions? Yeah.
Hi. So generally, you consider you want some symmetry and intelligence, and then you're going to go back to a symmetry in the universal Turing machine, right? So that's the general framework, and you can imagine that there might be a kind of an abstract version of this result, right? Like maybe you have a set of possible requirements that you might want to impose on your intelligence measure, and then you're going to go back to enforcing that you should be able to enforce a symmetry on the universal Turing machine. So maybe something like translation invariance. I don't know if that follows from the reward symmetry. Does there seem like there's some hope of finding the minimal set of requirements that would allow you to do that translation, the minimal set of requirements that you used in this work for this symmetry?
I don't exactly understand the question. You mean a minimal set of requirements on U such that K of mu bar ends up equaling K of mu? Is that what you mean?
No, I mean in general. So okay. So if I want to use a symmetry on the intelligence measure to enforce a symmetry on the universal Turing machine, how generally can I do this? How generally do symmetries in the intelligence measure map to symmetries in the universal Turing machine? And do you think there's hope of answering that question?
Oh, that's a good question. I haven't thought about it much, but one thing I can say, and it's sort of anticipated by this example about the French and English text, is that if you are desiring that the intelligence be fixed by a function which has the property that f to the k of x, by which I mean f applied k times to x equals x for all x for some fixed finite k, then you would be able to constrain the UTMs and obtain such symmetries, and that would translate to symmetries in intelligence. For example, with the permutations, because the action space is finite, at least the way that Marcus and I formalize RL, because the action space is finite, the set of permutations on the action space is finite. And so there's only finitely many different things you need to worry about. And that's why it is possible to transform any given prefix-free UTM into a C permutable UTM, because there's only finitely many permutations. Let's say there's n permutations. So you could create a new programming language from the original programming language where every program in the new programming language starts with k bits, where k bits is enough to specify this program is intended for the version of RL where such and such permutation has been applied. Now, if we were dealing with infinite spaces of permutations, then we would not be able to use that same construction. We could, of course, create programs which start with strings of bits that specify arbitrary permutations where the permutations are unbounded, but without a way to bound the lengths, this would not preserve the complexity of the resulting programs, which is the whole point. So I think what we know right now is that if the functions that you want to create symmetry for, like the f, which translates English into French and French into English and undoes itself if you apply it twice, if those spaces, if it's finite how many times you have to apply f to get back to the origin, then you can induce the symmetry. And we haven't looked into translations where there are infinite orbits. And I'm skeptical that you would be able to easily obtain symmetry results for transformations or translations, as you called them, which have infinite orbits. The translation on this slide here has an orbit of length 2 because f of x equals x for all x.
Yeah, okay, I see. Thank you. That's interesting. Discussion.
Oh, this. Yeah. Is that question online or I don't see? Oh, sorry. Oh, yeah, okay, yeah, so you can unmute James Bowley.
Yeah, I had a question about the utility function of the sequential decision theory half of AIXI's contribution to the measure of intelligence. That's a open parameter in AIXI, just as is the choice of universal Turing machine. And the first bit that provides positive or negative, of course, does not completely specify the utility function of SDT. If you specify the utility function of SDT to be the minimization of the length or minimization of an approximation of a Kolmogorov complexity, you have a intelligence seeking agent that's looking for the Kolmogorov complexity of the very environment in which it's operating. If you see what I'm saying, in other words, you're getting to some kind of a closure without necessarily having a complete specification of the UTM or of the Kolmogorov complexity. And this seems like it might be a top-down way of approaching an intelligent search for Kolmogorov complexity itself, as well as the UTM. Have you looked at that kind of a closure?
Well, I haven't looked at that very much myself, but I know that a lot of work has been done on trying to find UTMs with inherently desirable properties. And I know a lot of this work has run headfirst into a wall, and basically the conclusions have been, we can't figure out any desirable properties for a UTM that are inherently desirable. And that's part of what makes Marcus's and my paper interesting, is that although it's only for the RL context, and people outside the RL context would vigorously hate you if you required every Python program to start with a bit specifying whether or not RL rewards are positive or negative. But within the RL context, this gives you intrinsically desirable properties for UTMs. And so I think it's a baby step in the search for desirable UTMs. And I hope that's what you're asking about, is whether this applies to the search for inherently desirable UTMs. By the way, what does did you say SVT? What does SVT stand for?
Oh, SDT, sequential decision theory, is the thing. AIXI, as I understand it, is a unification for a relatively parameter-free model of universal intelligence between Somalov induction and sequential decision theory. And sequential decision theory has an open parameter of the choice of utility function.
Yes, perhaps Marcus would like to speak something to this. I think I don't understand the question very well. But
well, the last bit I understood with the question that it requires was relative to utility function, but that comes always up. And where do the rewards come from? So I keep it very short. So from a scientific perspective, you don't have to the IXI model is fully defined, and its rewards come from the environment. So in the IXI model, there is no reward function or utility function. It's just a reward channel. And then, of course, once you apply it, these rewards have to come somewhere. But either it interacts with the humans, and the rewards come from the humans, or you shortcut it to something intrinsically universal, like information gain, right? Or you shortcut it towards something very specific if you have a specific task in mind. But that's probably a longer discussion. But sort of the IXI model does not need to specify the utility function, as it also doesn't specify where the observations come from.
Right. Okay, thank you very much for the time.
All right, okay, thank you everyone. So yeah, for those online, we'll thank you for coming and see you tomorrow. And the meeting.